to start with the agenda. And I also wanted to start with giving you these slides in Slack. So the agenda is what you see in front of you right now. The TLDR will briefly go over what kind of trees are. If you want to learn more, I have way more information on this GitHub page. We're then going to go through an easy problem. Here I have the link to the actual problem and an answer in Python. And then medium problem. With 40 minutes, I'm guessing we're going to get to medium. So here is the LeetCode and here is the answer. So you could follow along while I'm doing it. The hard problem I'm going to try to get to in 40 minutes, but we may not be able to. So please note that this is there, and the answer not only has the answer, but I have like a lot of information of how we get to the answer. Now, I am solely doing iterative approaches during this this talk. I previously did a recursive approach for Women Who Code about 4 years ago. Since then, I realized iterative approaches are actually better for interviewing. So I'm trying to focus on just doing iterative approaches when I am doing DFS and BFS for talks now. Lastly, there's also a page to add me on LinkedIn. I do not accept people I don't know. So if you would like to add me, please make sure you have the note Girl Geek X. If for any reason you lose the link, you can go to my, the link to the slides. You can go to my website and you can find them here. Two quick call outs on my website. I also have a section for those of you who want to know more about how do I do coding interviews well. There's an entire section on how to study, where to study, and all of that kind of stuff. So these are some of the resources that I'm trying to give you all because there's a lot. We won't get to all of it during this discussion. So I want to make sure that it is useful for you all. That's why I'm going to start with basics. I'm going to start with an easy problem, and then we're going to move on to a medium problem. Please feel free at any point to ask questions. I am doing my best to look at the chat, but I believe you also may be able to unmute. Angie, correct me on that. It'd probably be easier for me to hear you if you unmute and say, hey, wait, what happened? Alrighty, so again, please feel free to ask questions at any point. So let's start with the basics. This whole page is about trees. Some of the terminology, if you've never been exposed to trees before, nodes are huge. And this is where we talk about children, parents, siblings, neighbors. There's all kind of relations. Important to us today, we're going to be talking about depth and height. There's a bit more basics here. I have an example of like trees versus grass. Today, we are specifically focusing on binary trees. There are some different approaches depending on if you have a binary tree versus an n-ary tree. And so today we are focusing on binary trees. I also have a lot of useful kind of diagrams and photos in this. But if at any point today you're like, I don't understand what we're doing, I also have a drawing pad here so I could draw things out for you. Sometimes that is more helpful. There's also different types of approaches. So let's go to BFS, stands for breadth first search. Two important things that I recommend you just memorize when doing BFS iteratively. You want to use a queue, and it's for things when you want to solve problems where you go level by level in the tree. There are a bunch of examples here of how you implement different types of BFS. Now, DFS, we will be for at least the easy problem and the medium problem. We will be doing DFS for both of them. If you want, I can also do BFS for the easy problem, but BFS does not work for the medium problem. So DFS, some things to memorize. You're using a stack if doing it iteratively. And it's often associated with height, like depth is deep, going as deep as you can. So here are some other examples of how to kind of do all the basics for DFS. And then I'm going over specific types of DFS. There's in order, there's post order. And the orders basically talk about, am I doing the left node first, the root node, or the right node? And again, those are things I would just memorize. Let me see if there's anything else on here we need. So there's summary diagrams, and I recommend reading this in without a dark mode so you could see my summarization of the n-ary trees. Okay, so before we move on to the first problem, I'm going to let you read it and then just give you a moment to read it, and then we'll start working on it together. Okay, so any questions before we move on to actually doing the solution? I'm not seeing any. When I look down, that's me looking at the chat. I'm not seeing any, so I'm going to start. First, what is this question asking? I want to be able to tell if given two different binary trees, are they the same? And so when you have them written out like this, it's way easier to see, right? These examples are very helpful. And often with trees, writing things out, diagramming them are very, very helpful. And so I always begin with pseudocode. Before you write anything, make sure you are understanding the problem. And so I'm going to start this with a depth first search solution. Once I solve this, we can decide if we would like to move on to the breadth first search solution, or if we would like to go on to the harder problem, or if we would just like to ask questions. But to begin with, we are going to do the depth first solution. Okay, so a few things. When I hear DFS, I think queue. So I know at some point I'm going to need to create a queue. And after I have the queue, I know that at some point I am going to have a while loop because I'm going to have to do something with that queue. When you have queues, you generally have to pop from them to evaluate things. So I know I'm going to have to pop from the queue and do something with it. So when I do something with the queue, there's generally, like, you have to take like a base case. I don't know if you've heard that. When doing LeetCode, make sure you always take the base case. And this is kind of where you check for like existence. Generally, once you've done the base case, you're generally comparing values. And once you have done the comparison of values, you have to keep adding to the queue. Okay, so generally, this is how DFS will work. So let's look at what our problem is, and let's see, how would we do this? Oh, wait, hold on. I think I was looking at the wrong notes for DFS. Am I looking at DFS or am I looking at BFS right now? 1 second, let me look at my notes. Sorry, I was looking at my BFS notes. Let's see. DFS is, I put Q on here. So sorry, this is stack not Q. So sorry. My notes are very close together. Okay, but everything else holds. You are going to still have a while loop. You're still going to pop. You're still going to have a base case that tests existence. You're still going to compare values, and you're going to keep adding to the stack. So let's start with actually implementing a solution. So I know I need to create a stack. So let's start coding that. And generally, when you create a stack in Python, you're going to do it in an array. And now, what is my stack going to include? I'm going to have both of my nodes together. So the way I want to kind of rename them, I'm going to do node P. That just helps me for clarification. Node Q. So I have node P. That's what I'm starting with. And I have node Q. Now, I have a while loop. Okay, so I want to pop from my while loop. How would I do that? Very easy. Actually, I'm going to keep these the same up here, and then I'll name them below. Do I have to have? Okay, so I'm going to pop here, node P, node Q. So it's whatever node is part of P and whatever node is part of Q, the trees right now. And then very easy, stack dot pop. And so this will give me, because the first one is P, it'll give me what's related to P. The second one is Q, it'll give me what's related to Q. So we have a base case. So what is our base case? Our base case could be that neither exists. So if node P is none and node Q, second, is none, we're going to do something, okay? However, if node P is, what are we looking at? Let me look at the. So if they are the same, that's awesome. We'll do something there. But if one of them is none and one of them is not, that means that they are not the same tree. Then we would return false. And so I'm also going to put return true outside of the stack, because we know that if we don't return false at somewhere in the stack, we're going to return true. So once I kind of get this worked out, we'll work through it and we'll go through all the loops. So here we are, and we're about to compare values. So I have tested a base case. Now, how am I comparing values? Well, we know that the tree is defined up here. So in order to see the value of the node I am on, I have to call dot value on it. So I want to know the P value. So let's do current P value. And I get that by doing node P dot value. And then I get the current Q value by doing node dot Q dot val. And then you want to compare them. If current P value does not equal current Q value, then we're going to return false, because they're obviously not the same. So what happens when you compare your values? You need to, sorry, what happens after you compare your values? If there are nodes, you need to keep adding them to the stack. And so we're going to stack dot append node P, and I'm going to leave this one blank right now. We're going to fill it out. Right or left. And then we're going to do node Q right or left. And then I'm just going to copy this. So this is where the traversals for DFS come into play. We need to make sure that we're pushing in the right order. So we want to always make sure we're evaluating the leftmost child first. So that means if you are using a stack and you want to evaluate the leftmost child first, that means you have to actually push the right child first. So here we are going to update it. Right. Right. So that means that the right children will go on first and the left will go on next. So when I pop from my stack, I will always get the left children before the right children. Okay, so now I think I have the basics of what's going on. So now we're going to do example 1. So you can walk through with me. Example 1. So the input for example 1 is P equals 1, 2, 3, and Q equals 1, 2, 3. So this is output true, okay? So we should get to the return statement on line 35. So let's do it. We are starting with the stack. So what will our stack look like? Our stack will look like stack equals, and remember this, the numbers I'm using are representative of the node itself. They're not like an actual number in an array. They are all representative of this tree node up here. So it's a structure that has a value and potentially a left and a right. So when I write something like this, please know that I'm referring to the node at 1 and the node at 1 as well. So Q node root node is 1 and Q root node is 1 and P root node is 1. So now we're going to get into the while loop. It is time to pop. So I also like to know how many times I've gone through the loop. So I'm going to put loop 1 right here. So I am popping. And when I pop, these are my results. Node P equals, what is that? 1. Again, node with root value of 1. And node Q equals 1. Node with root value 1. So next we go on to the base case. So base case. Let's look at here. Node P is none and node Q is none. Are either of these none? They are not. So go to next statement. Okay, here's the next statement. If node P is none or node P is none, you immediately return false. This is, oh, hold on, and this is false. This is also false. So go to next statement. Okay, so now we are going to compare values. So we know that current P value equals 1. Current, sorry, my dogs, if you can hear them, value equals 1. So if current P value does not equal current Q value, then we would return false. Okay, but this is false. So that means go to next statement. Okay, so our next says keep adding to the stack. Okay, so let's do this. We're going to add rights. So we're going to stack.append and node P right. So let's look at node P right. Node P right is 3. So I'm going to add 3. And I'm going to, again, for node P left is also 3. So I'm going to add that. Now I'm going to add lefts. Stack.append. I'm looking at left for P is 2. And left for this is also 2. So fantastic. We have added our nodes. And we're going to start our next loop. Loop 2. Okay, so we have while loop. And remember, we always want to pop left. I'm just checking to see if there's any comments yet. No. All right, so we're popping off left. So remember, pop from the left first. So we want to pop the 2s. Ooh, that's too many O's. Okay, so what do we do? Pop. Node P is going to equal 2. Node Q is going to equal 2. Okay, so next statement, we're going to look at these. I'm going to copy and paste. So node P is not none. Node Q is not none. So that's false. We're going to the next statement. Both node P and node Q have values. So we're going to continue to the next statement. And then we're going to compare values. Okay, so let's compare the values. So current P value equals 2. Current Q value equals 2. Fantastic. Then we're going to keep adding to the stack. So now we're going to add rights and we're going to add lefts. So let's add rights. So we are looking at right now, remember we were at, which one is first? Node P is first. So here's node P and we're looking, is there a right? There is not. So we would add node P dot right, node Q dot right. But note, these are going to get added as none and none. And then we're looking at, oh, sorry, that's the left. I was doing, this is right, this is left. Sorry, y'all. So now we are going to be adding the left. So left is this way. And so we're doing node P dot left and node Q dot left. And so again, note right here, you're basically adding none and none. So something I didn't do up here, which I probably should have done, was how does the stack look now? Okay, so this is what our stack now looks like. Stack equals, we're having 3, 3, 2, 2, and then this is what our stack looks like here. Okay, all right, so loop 3. While loop. We're always popping, right? So let's pop. Pop equals node P equals 2. Node Q. Oh, sorry, none. Next one. None. Node Q. Where is it? Q equals none. All right. So if node P is none and node Q is none, we have to do something. So this is true here. So we have to do something different. And now, what do we have to do? That's important. Now, if they're none, what do we do? If they're none, we've reached the end of that parent's child. And so we're basically going to continue on, and then we're going to do the compare value. Oh, sorry, we're going to continue to the next loop because there's nothing to compare. They're both none, and they have no children, so there's nothing to add to the stack. So let's now go to loop 4. While loop. Again, we're popping. That's how stacks and queues work. And again, oh, I forgot to show you what the stack looks like here. So let's update the stack here so that you know what we're working with. Okay, so popping. Let's pop node P, none. Node Q, also none. And like loop 3, we're going to hit this statement. Okay, we're going to hit this statement. It's going to be true, and it's going to mean continue. So what does the stack look like on this loop? It is now going to look like this. So as you can tell, we're getting closer to our final loop. So loop 5, while loop. Again, we are popping. And what are we popping? We're popping those 3s. So node P equals 3. Node Q equals 3. All right, now we are going to look at this again. These are not true, they're false. So when they're false, we go to the next statement. And then we're going to look at the next if statement. This is again false. So we're going to continue to the next statement. And now we're going to compare values. So current P value is 3. Current Q value is 3. They are equal. Yay. And then now we look. Do they have children? Okay, so we're going to add rights and we're going to add lefts. And because they don't have children, I am just going to kind of copy from the above. Rights. Oh, and I want to make sure this all looks good for y'all. All right, so we're adding this. So what does our stack look like right now? Our stack looks like this. Okay, now because, oh, sorry, forgot one set of nuns. We've seen a set of nuns before, so I'm basically going to copy, I think it's, where are we that we had them? These two. I'm going to copy these loops. So we're going to loop again exactly like we did before. And this is going to be loop 6. What does the stack look like now? This one. This is loop 7. The stack now looks like this. So we're going to stack is empty, exit loop. And when you exit loop, you return true. So that is how we know that this first example is an actual same tree. Now, I want to be mindful of time, doing a time check. I think we have about 12 more minutes. I want to ask you all, would you like to see just that this solution works by me submitting? Would you like me to do the example line by line, for example, 2 to show how false would work? Or would you like me to either move on to the BFS solution of this or the house robber problem? Someone could state or like put in chat. I want to make sure that I'm using the time as best fit for all of you. House robber, okay. Okay, so I saw a question real quick. Okay, we'll move on to house robber. Okay, real quick, Coriano. Question, how do I approach LeetCode challenges I am unfamiliar with? I use find.com. I post, I'm writing this in the notes, that's what I'm looking down, or in the chat. I post, I use find.com, get a real answer, and then ask questions until I understand what is going on. So find.com is like one of those like ChatGPT, Claude type things, but for code and developing. And so when like I'm just confused out of my mind about something, I'll just take the solution and then I'll just ask questions and questions and questions. It's like having a tutor. And I recommend use any of the Claudes. They have 2 different Claude versions with find.com when asking questions. Okay, and then let's see. Oh, for done with recursion, please go to here where I solve it with recursion. This is the link to the full video, so you can see how to do all of these in using recursion. Okay, so now we're gonna go to the house robber problem. Always fun, always fun. Okay, so this one I have to do like, let's see, okay. Where are we on here? Just going through my notes. Okay, so this is a twofer, okay? I want to warn you all, this is a twofer. Not only are you doing binary trees, DFS, this one also requires you to do dynamic programming. I know most people hate dynamic programming, but I kind of also like it. Also on my website, I have like a dynamic programming YouTube video if you want to watch that, but I love dynamic programming. Okay, so this one you are going to need to do binary trees. We're going to do DFS, and I'll explain why. This one is dynamic programming, and I can explain why. Also, I see there are a bunch of questions going up in chat right now, so my time is up at the 40-minute mark, I believe, but I will still answer your questions in chat after that. Okay, so house robber. We're doing binary trees, DFS, and it is dynamic programming. Now, I'm just going to give you a definition because this is very important to solving this problem, and you may or may not have heard of this before. Memoization. I'm going to read it. Memoization is an optimization technique that speeds up programs by caching the results from expensive function calls and returning the cache result when the same inputs occur. Now, if that doesn't make any sense to you, go to findphind.com, put that in, and then ask it questions until it explains it to you in a way that works for you. We all learn differently. So like, I think that's a beautiful thing about having find.com, because you could just ask it targeted, pointed questions that are aligned with the way you think, and you can get the answers returned in ways that will help you progress. Okay. So reminders, DFS, we use stacks. Okay. So this might be a little confusing to some of you because generally DFS is kind of thought of as top down, meaning you're going from the root all the way down to like the leaf node. But our dynamic programming has approaches too. And so we're traversing the tree from a top-down approach, but we're computing our answers from a bottom-up approach. So just so you know, when you're looking at my notes, I do have the answer in there. I put that we're using DFS, but I do also have, I believe, bottom-up in there. And so DFS is referring to how we traverse the tree. And bottom up is how we are computing, aggregating the results. Okay, so house robber. The thief has found himself, there's various house robbers, but basically, what's the maximum amount of money we can get? And so the goal here is to figure out, typing on the wrong thing. Okay. Steal from roots and its grandchildren, or steal from children of roots. Now, why is this? We know that here's the root. We cannot steal from its children, right? Because that will alert the police. So we have to skip the children and go to the next row or the next group, their grandchildren. So we need to figure out, can I get the most money from doing root plus grandchildren? Or can I get the most money from doing the children of the root? So here's an example. We're going to the grandchildren and the root gets you your most money. Here's an example. We're stealing from the children of the root gets you your most money. So that's the basic idea of this. Again, when you have way more than, what is this? There's like 6 nodes, it gets more complicated. But as always, we are going to start with pseudocode. Okay, so pseudocode. I have 5 minutes to pseudocode this with you. I don't think we're going to get all the way through. But again, I have all of the answers in there in this thing that I sent to you all, and I will take questions after my 5 minutes ends. All right, house robber. Okay. So what are some of the things we're trying to do? We are looking to get houses with max profits. You always want to name things better. I'm okay with things being multiple words because that makes more sense to me than like HP. So that's just me. I like verbosity. And then because we're doing DFS, is we're going to stack. And you always got to start with something. So we're starting with something. And then I'm just going to use that and I'll explain to you. So we're starting with, we know we have to memoize. This is memoization here. We know we have to memoize for dynamic programming. And we know we're doing DFS. So we know this is a stack. And we also know that we're going to have a while loop, right? We always have while loops. So we're going to say while stack. And then here's something that you may or may not have heard before. These kind of problems often need something called peeking. If you haven't heard of peeking before, it's kind of looking at what is in the stack before popping it off. And so this is how you peek. Where is it? Node equals stack. Love Python. So easy, so simple, everything, especially for LeetCode interviews. That is how you peek. So for example, my root would be here. And then I would look at, again, remember, this is not the actual, this is the whole structure of the tree node. So I would look at what the last thing I added was, and that would be the root node. So when I peek here, I'm going to get 3, and this 3. Okay, so then we're going to do some logic. Does node exist? Okay, because you can have none. We saw that in the last one. Okay, if the node exists, is this node, sorry, I'm trying to think of how to explain it to you. Is this node already in here? Have we accounted for it in memoization? Okay, so that's the first thing we check. I'm trying to make sure that I'm putting it. Okay, because if it's not, we can kind of move on. All right, so first, is this node already in house max profit? If it's there, I'll put this. If already there, we do nothing. If not there, we do something. Okay, and please note, these are the specific nodes themselves. You can see here that this is a 3, this is a 3, this is a 3. You'll see 3 multiple times when I'm like kind of working out the problem in my results, but you will not see it. You will not see it as that. They're different 3s. They're each the specific node, and 3 is the value of that tree node. Now I have 1 minute to go, so I am going to really quickly just put up the answer for this one. Okay, so this is what the answer looks like here. I do my best to kind of explain what is going on. And then here's where I go through all the different loops. What I recommend, because my time is up soon, I recommend giving this to find.com. So let's go to find.com. Okay. And then let's copy it in. Okay, so I'm putting it in there. That's going to take, oh, that's not the model I recommend. Okay. Oh, look at it, it's even improving my solution, okay? Oh, I don't like that. It's making all the names smaller. Okay, can you explain to me why, and let's look at something that I want to check. Why am I peeking? Can you explain to me why I am peeking? Okay. And so you can use the example I've given you with the answers to explain to yourself, to try to understand more. And so look at find is going to give you, this is what's happening. Oh my God, there's a sequence diagram. Oh my God, there's words. And then you could keep asking it questions until you understand peeking or some of the other things. Also, if it's not like easy enough to understand, be like, hey, that didn't make sense. Tell me again. And again, I really recommend that you use Claude Sonnet or Opus. That is my time. I will take questions now. Thank you all. I'll start answering questions.
Thank you, Krys. She'll be in the chat. We're going to be moving to our next speaker.